Hello everyone and welcome to MV Tutors. I'm Tilo and I'll be looking at the photoelectric effect with you guys today. Please don't forget to like our videos as well as subscribe to our channel. And while you're at it, please just click on the notification button so that when we upload more videos, you are aware and are not left behind. And guys, for those who want to do or want to have a private lesson, please do book on our website www.mvtutors.co.za. So, what is the whole point of the photoelectric effect? Well, basically, it explains why light with the right frequency can eject electrons from a metal surface. And you'd ask yourself, why? Why do you want to eject electrons from metal surface? Like, why? Well, one of the applications of the photoelectric effect is now with solar panels. Okay, so because we have an unreliable source of electricity here in South Africa, load shedding, load reduction, and the likes, we have to look at alternative sources. And I mean, we have the sun at our disposal. Africa is known for the heat, right? So why not use the sun to create electricity? Or, yeah, so that is what you would use it for. Okay, now here I've drawn a light bulb, and basically I've showed that when light is shone, okay, it has two properties. You have the waves, okay, you can see the waves there, and you also have particles. So we can then say that light has a dual nature. Okay, so light exhibits a dual nature, and firstly we have the wave nature. And if you were to refer to your grade 10 and 11 work, you would see that light can be reflected, okay, it can be refracted. So refraction would be if you have light in air and then all of a sudden it enters water, so changes direction and all of that. And then we have diffraction. So diffraction, when you have wave sources coming together, when they come together they either create a bigger wavelength, okay, or they have a smaller wave, like maybe smaller amplitude, or they just cancel each other. So that's basically diffraction. So light exhibits either a wave nature when it is propagated. You'll see that word a lot, propagation or propagated. So that means it's transmitted. Okay, and also light has a particle nature. Okay, and that's the part that we're going to learn about with the photoelectric effect, that it's not just the wave nature that light has. There's also the particle nature, okay, and light actually comes traveling in packets of energy, and those packets of energy are called photons, okay. And this particle nature, we see it when it strikes and interacts with other matter, okay. Hence we say that when light maybe strikes a metal surface, it would eject electrons. So that is basically the particle nature of light. But we need light with sufficient frequency, and frequency would refer to the wave nature of it. Okay. So then we get to define what the photoelectric effect is. Basically, it's a process whereby electrons are ejected from a metal surface when light of suitable frequency is incident, or it is shining, it's shone on the surface. And I've also given an example there, as I've explained, that solar panels are used to generate electricity. Okay, so this light that has particles, these photons, okay, packets of energy, if you would say, if you prefer. So light consists of these photons, okay, and each photon carries a quantum of energy dependent on its frequency. Okay, so again, frequency refers to the wave nature, and the photons refer to the particle nature. So each photon, okay, comes with energy. This energy, we call it quantum, and it is dependent on its frequency. Okay, so the photons, they propagate. Another word for propagate is to spread. The photons spread through space at the speed of light, which is very important, okay, because the speed of light, we get it with this equation, C, I think I wrote it somewhere here, yes, C, okay, this equation over here, C is equal to lambda, which is the wavelength times frequency. Okay, so now we said that these photons have energy, okay, called quantum, and that is represented with this E over here. And then that will be equal to h times f. H would refer to Planck's constant. Okay, this is given in your formula sheet, so you don't have to cram what h is, but there it is, 6,63 times 10 to the power negative 34 joules seconds. Okay, and then times the frequency, and that would be the frequency of light, which is measured in hertz. Okay, and another way of rewriting this equation, so we have frequency over there, right? So because we know that the speed of light, c, which is actually 3 times 10 to the power 8 meters per second, is actually equal to the wavelength times the frequency, we can then write our energy equation in terms of the wavelength. If you've been given wavelength, you would write it in terms of the wavelength, and this is how it looks. But if you've been given frequency, you can use this one, this equation over here. All right, so now we're going to talk about, we're going to define some terms. All right, so what we have is the work function, which is W subscript 0 or O. Okay, and what is the work function? Basically, that is the minimum energy. Okay, so it is energy. Remember, energy is measured in joules. So it is a minimum energy required to emit or eject an electron from a metal surface. And that minimum energy is really dependent on the type of material that you have. So we have unique work functions based on the type of metals that you would have or type of materials that you would have. So it's a unique number to each material. All right, then we also have the cut-off frequency, or what we would call the threshold frequency. I see in many exams they actually refer to it as the threshold frequency, but it's good to know both terms. And again, that would just be the minimum frequency required, or minimum frequency of light needed to emit or eject electrons from the metal surface. Again, with this minimum frequency, it is also unique to each material. Okay, so that is quite important. And then it says at the threshold frequency, all the energy of the photon is equal to the work function. Okay, basically, guys, we're talking about minimum energies or minimum frequencies required to emit an electron. So it's at a minimum. Okay, so at this point, the electron is not moving yet, it is just ejected. So you have a metal surface here and you have energy, and it's like it woke up. It hasn't started moving yet. So therefore we say that at the threshold frequency, all the energy of the photon is equal to the work function, the minimum energy. And the kinetic energy of a photon is 0 joules at that point in time because it hasn't started moving yet. It just woke up from rest. Okay, and therefore we have our equation where it says the work function is Planck's constant times the threshold or the cut-off frequency. Okay, so basically if you were to like yeah, that is it. So now we get to the next step. So the electron woke up from rest, and now once photon energy is absorbed, some energy liberates the electron, so it just wakes up the electron, and the rest contributes to the electron's kinetic energy as a free particle. Okay, so yes, so once the photon energy is absorbed, like we said, we have energy reserved for waking up the electron, and it's just sitting there like, okay, I'm awake now, and the rest of the energy contributes to the electron having kinetic energy. So now not only has the electron woken up from rest, but now it can get to work. Okay, so now we redefine our formula. Okay, so the energy of a photon, like we had talked about before, is equal to Planck's constant times frequency. Okay, and what does that translate to? Well, basically we have the work function, which is the minimum energy required to eject an electron, to wake it up. Okay, and then we have to add it with the maximum kinetic energy. Okay, it's going to require the maximum kinetic energy to get these electrons moving so that electricity can be generated, for one. Okay, so we have defined the work function as Planck's constant times the threshold or the cutoff frequency, and we know that kinetic energy is equal to half mv squared. MV. MV tutors. So m would be the mass of the electron, okay, that is provided for you in the formula sheet, and also the maximum velocity squared. Okay, again, when you have the energy of the photon, you need the energy to emit the electron as well as the energy to get those electrons moving. So actually, if you looked at this equation where the energy of a photon is equal to the work function plus the maximum kinetic energy, I drew a graph on the right here. It would actually tell you, or rather it has that straight line form, okay? So basically, if you were to have the y is equal to mx plus c, okay, how could we relate that? Well, if you made the kinetic energy, the maximum kinetic energy, the subject of your formula, you would then have that your work function, your energy of the photon, you subtract the work function. Okay, so basically your C value where it crosses the y-axis, that would be your work function. So over here, you would have this point over here, that would be your work function. Remember, work function is the minimum energy required to eject an electron from the metal surface. Okay, so that's work function over there. And then your gradient, which is Planck's constant, that would just be h. Okay, so your gradient, that's Planck's constant. And then on the x-axis, you would have your frequency. Okay, so that would be, it crosses the x-axis there. So basically that would be your frequency. All right, and this would actually be your minimum frequency. Okay, your threshold or cutoff frequency. Okay, and as you go on ahead, you are going to actually get the proper frequency. Okay, as well as the energy associated with that frequency. Okay, kinetic energy with that frequency. And what have you have left? Okay, on the y-axis, that would be your maximum kinetic energy. So you can relate that really to a straight line graph. If they were to give you this graph in an exam and they tell you what is the gradient of this graph, you would know it is Planck's constant. And if you have like these lines for different metals, you'll see that they're actually parallel to each other, right? And why is that? Because the gradient is the same. It's literally the same. Remember, with parallel lines, you have the same gradient. It's the same because you have Planck's constant there. Okay, so that's just something to bear in mind, think about, know as well, because it does come in handy. We're going to have a look at the condition of emission of photoelectrons. Basically what I was describing in words, I just want to show you how it actually happens. So if you have your frequency of light less than your threshold of cutoff frequency and your energy is less than the work function, nothing will happen. And it doesn't matter if you intensify your light, still nothing will happen. Okay, you really need suitable frequency as well as the minimum energy. So in the first case, photoelectrons are not emitted. In the second case, you have the frequency of light being equal to the threshold frequency. And also the energy of the light equal to the work function. So once you shine your light, okay, or yes, light is incident on the metal, what do the electrons do? They wake up like, okay, what do we have to do now? But at this point, they cannot move yet. They just literally woke up, okay? They're not moving yet. All right, so yes, photoelectrons are emitted onto the surface, but they are not moving anywhere. Then the third case, where you have the frequency of the light higher than the threshold frequency and your work function, the energy of the light higher than the work function. So in this case, the photoelectrons now, not only are they ejected, but they are now emitted from the surface. Like I'm saying the same thing. Not only are they ejected or emitted from the surface, but they start moving. They have kinetic energy. They can go and now work. and do what? Produce electricity or generate electricity. Okay, so that's basically what happens. Now let's talk about, I've mentioned the intensity here in the first part, that even if you intensify your light, make it brighter, still that is not enough to get the electrons emitted. So let's see, what is the difference between intensity? If you increase intensity or you increase frequency, what does that actually do? Okay, so what happens when you increase the intensity of light? Basically, what happens when you increase the brightness of your light? Okay, so let's say you had enough frequency to eject the electrons, you had enough energy to get the electrons moving. So everything is in, everything is in motion. But now you decide, let me increase the intensity of the light. What does that do? What it does, it increases the number of photons hitting the surface. So the brighter the light, it means you have many packets of energy, many photons being emitted. Okay, no, not emitted, but hitting the surface, allowing many electrons to be emitted. Okay, so by increasing the intensity of light, you are increasing the number of electrons that will be ejected because there are more photons hitting the metal surface. Okay, so all of that is happening at a higher rate. So you intensify the light, it's shining brighter, more photons are hitting the metal surface, and electrons are also being ejected or emitted at a high rate. Okay, a lot of them are emitted per second. Okay, and like I said, the rate is also increased. That is something, guys, when you do the multiple choice section, they play with you with that. You have to understand what does it mean when you increase the rate? How does that even affect? If they talk about current, remember current, that is actually, charge over time. Okay, the change in time. All right, so time here would refer to the rate. So if your rate is increased, they would ask, what would then happen to the current? Will it increase, or will the ammeter, have a higher reading or a lower reading? So you need to relate all these things. Okay, so just to summarize, the brighter the light, the higher the intensity, the more photons hitting the metal surface, the more electrons emitted at a higher rate. Rate, you can relate it to current, okay, through charge over time. Okay, so here we can see that indeed the energy of the photon is definitely bigger than your work function. Now let's talk about the frequency here when it comes to intensifying light. Well, basically the energy of your photons, like I said initially, you have enough frequency, you also have enough energy, right, to eject and also have the electrons move. But intensifying the light does not change the energy of an electron, guys, or the photon. It doesn't change the energy, so the energy and the frequency, they remain constant. Okay, therefore the kinetic energy of the electron will also remain constant, as well as the velocity, the speed, they remain constant. So intensifying the light, it has to do with the number of photons hitting the metal surface, as well as the number of electrons being emitted. It has nothing to do with the frequency or the energy or the kinetic energy, as well as the speed. Those remain constant. Now let's get to the frequency of light. So what if you increase the frequency of light? Well, if you increase the frequency of light, you will be increasing the kinetic energy of the electrons emitted. So let's say you had enough frequency and then you had enough energy to emit the electron. So it's all moving, everything is in motion, but now you increase the frequency. So the speed and the kinetic energy of the electrons emitted will increase. Okay, but that doesn't mean that you're going to have a lot of electrons emitted. No, it just means the electrons will have a higher speed. So you still have the same number of electrons. Yes. So you still have the same number of electrons that are being emitted, and also you still have the same number of photons striking the surface. And yeah, so basically the rate at which electrons are emitted, that remains constant. Okay, So intensity has to do with number. Frequency has to do with speed. Intensity also has to do with the rate, okay? But frequency, the rate remains constant. Okay, so I hope that makes sense. And we can then, the last part that I mentioned here is, oh, my nose is so itchy. So sometimes they give you energy in terms of electron volts, which is EV, okay? And we are used to energy being given in joules. So what you must do, if it's given in electron volts, you need to apply a factor, which is equal to the charge of an electron, and then you can get it to joules. So the charge of an electron is 1.6 times 10 to the power minus 19. Okay, so now we're going to have a look at an exam question to see how they actually examine you on these types of questions. Alrighty, so I got a question from the 2018 paper, question 11. Yeah, let's get to it. So it says, a group of students investigates the relationship between the work function of different metals and the maximum kinetic energy of the ejected electrons when the metals are irradiated with light of suitable frequency. Okay, so 11.1, define the term work function. Okay, we've been saying this a lot, but work function, basically that is the minimum energy required to emit an electron from the metal surface. Okay, and then what do they tell us? During the investigation, ultraviolet rays of wavelength 2 times 10 to the power minus 8 meters are allowed to fall on different metal plates. The corresponding maximum kinetic energies of ejected electrons are measured. So they give us the maximum kinetic energies of silver, potassium, and lead. All right, and now 11.2 says, write down the dependent variable for this investigation. Okay, guys, remember that y is equal to mx plus c graph I drew? Okay, so in my mind, I'm thinking of the graph where you have the kinetic energy versus your frequency. So your dependent variable will therefore be, so dependent variable will be your maximum kinetic energy. All right, and then 11.3, write down one control variable for this investigation. So in this case, the control variable or the independent variable, I would say it's actually frequency. Okay, and since frequency actually relates to wavelength, you could also say wavelength. But remember, they are inversely proportional. All right, and then 11.4, using the information in the table and without any calculation, identify the metal with the largest work function. Okay, so what I'm going to do, I'm going to write the equation, okay, that relates the maximum kinetic energy and work function. So we know that the energy of a photon, okay, is equal to the work function plus the kinetic energy, the maximum kinetic energy. So if I made my work function, I know they said no calculation, but I'm just using the formulas here. I'm not calculating anything. So if I were to write the work function as the subject of the formula, I would then have that the energy of the photon minus the maximum kinetic energy of the electron. Okay, so what does that tell you? If this is my E here, okay, if I'm going to keep subtracting the maximum kinetic energy, the larger the maximum kinetic energy, the lower my work function. So the larger the maximum kinetic energy, the lower my work function. So therefore, if I want to get the maximum or the highest work function here, yes, the largest work function, I would have to look for the maximum kinetic energy that is the lowest. And in this case, that would be Yeah, because they're actually going from maximum to minimum. So I have lead first as the maximum and silver as the minimum. So the metal would be silver. And this is my explanation. Okay, I use the formula to derive to my conclusion, which is silver. Okay, so yeah, 3 marks should be sufficient. And then we have 11.5. Okay, they say use the information in the table to calculate the work function of potassium. So potassium has a maximum kinetic energy of 9,58 times 10 to the power minus 18 joules. Okay, that is the maximum. And then we have, remember they used ultraviolet ray to actually, the light that was incident on the metal, that is the ultraviolet rays. So the wavelength of it would be equal to 2 times 10 to the power minus 8. Okay, meters. So if I were to calculate the work function, oh, I already wrote this equation in terms of work function. Okay? So work function is actually equal to the energy of the photon minus the energy or kinetic energy, the maximum kinetic energy of the electron. So the energy of a photon, guys, remember E is equal to Planck's constant times frequency, but we have not been given frequency in this case. We have been given wavelength. So, remember C is equal to the frequency times the wavelength. So if you want frequency, you're going to get C over the wavelength. So frequency is C over the wavelength. So now I need to go get the constants, guys. H, I already forgot it, 6,63, ne? Something like that, yes. So we have 6,63 times 10 to the power minus 34. And I multiply by the speed of light, which is 3 times 10 to the power 8. Okay, and then let me just erase all of this. These are my side notes. Okay, so yeah. Okay, so now I have that HC over the wavelength. We have the wavelength. It is 2 times 10 to the power minus 8. Okay, and then they gave us the maximum kinetic energy, which is 9,58 times 10 to the power minus 18. Okay, I'm just going to get the calculator and then we're going to calculate. Okay, so if I put it in the calculator, I have 6,63 times 10 to the power minus 34 times 3 times 10 to the power 8 all over 2 times 10 to the power minus 8 and all of that we subtract 9,58 times 10 to the power negative 18. Okay, and we get an answer of 36,5 times 10 to the power minus 20. Okay, let me just put it up there. 36,5 times 10 to the power minus 20. We are calculating work function, which is energy, so it will be in joules. Okay, they didn't give us any electron volts, so we don't have to convert anything. Okay, so now we get to 11.6. We are there, guys. Thank you for sticking with me through it all. Alright, so state how an increase in the intensity of ultraviolet light affects the maximum kinetic energy of photoelectrons. Guys, we spoke about this. Intensity has to do with the number of photons that are hitting the metal surface. Then you get a lot of So you have a lot of photons hitting the metal surface, you'll have a lot of electrons that are emitted at a higher rate. Okay, that has nothing to do with maximum kinetic energy. If you increase the frequency though, you would have increased the kinetic energy of the electrons. So choose from increases, decreases, remains the same. Basically, it will remain the same. And everything that I have said, that will explain the answer. Intensity has to do with the number of electrons that are emitted. The higher the intensity, the higher the electrons emitted, because the more photons are hitting the surface. That's it. Intensity has nothing to do with kinetic energy or the speed of the electrons or the frequency. Okay, that is the reason. I hope you've enjoyed this lesson. I hope you've learned. And please like our videos, subscribe to our channel. Most importantly, share this information. Do not keep it to yourself. All right. Awesome.